Welcome to the Explainer. Today we're going to break down reinforcement learning. It's this really fascinating corner of AI where instead of giving a machine all the answers, we let it figure things out for itself, learning from its own mistakes and, of course, its successes. All right, so let's kick things off with a puzzle. How in the world do you teach a computer to win a game like Go? I mean, a game with more possible moves than there are atoms in the known universe. You can't possibly know the perfect strategy yourself, right? So you can't just program it in. Where do you even start? Okay, so here's how we're going to tackle this. First, we'll get a handle on what it means to learn without a rulebook. Then we'll use a super simple analogy, training a digital pet. After that, we'll lay out the official rules of the game, see how the stuff scales up from tiny tables to, well, powerful brains, and finally, check out where it's being used in the real world. Let's dive in. All right, Section 1, Learning Without a Rulebook. So let's really get into the why here. At its heart, reinforcement learning is built to solve a very, very human problem. How do you learn to do something when there's no instruction manual?
Think about it for a second. Traditional programming, it's all about giving a computer a strict set of rules to follow. Reinforcement learning totally flips that on its head. We don't tell the agent how to do something. We just tell it what the goal is. And from there, it's got to figure out the rest through pure trial and error.
Okay, Section 2, Training a Digital Pet. Now, to make sure this doesn't feel too abstract, let's use a really simple analogy that I think you'll get right away. So just imagine you're teaching a little digital pet a new trick. In the world of RL, your pet, that's the agent. Its worlds, your room or a park, that's the environment. The trick you're teaching it, like sit or fetch, that's an action. And the treat you give it when it finally gets it right? Boom, that's the reward. It's that simple. Positive feedback that just says, hey, that was good, do that again. All right, Section 3, the rules of the game. So keeping that digital pet idea in your head, let's get a little more formal and look at the actual framework. We'll use a simple little video game as our example here, a taxi trying to pick up a passenger. First up, we have the agent. This is our learner, our decision maker. In this little game, it's the taxi itself. And the agent exists and operates inside of an environment. For our taxi, that's this 5x5 grid, the city it has to drive around in. Now, at any given moment, the environment is in a specific state. You can think of a state as just a snapshot of everything that's happening right now, like where the taxi is, where the passenger is waiting, and where they need to go. So based on that state, the agent has to choose an action from a list of all possible moves. For the taxi, that's pretty simple. Move north, south, east, west, or maybe try to pick up or drop off the passenger. And this is probably the most important part of the whole thing. After every single action, the environment gives back a reward. Our taxi here gets a little negative reward for every step it takes. That's to encourage it to be efficient. But it gets a big positive reward, like +20, for a successful drop-off. And if it messes up, like trying to drop someone off in the wrong spot, it gets a penalty. This reward signal, it's the only feedback the agent gets to learn from. So all these pieces, the agent, the state, the action, the reward, they all work together in this continuous loop. The agent sees the state of the world, it takes an action, it gets a reward and a new state, and then it does it all over again, and again, and again. Over thousands or even millions of these cycles, the agent's one and only goal is to figure out the best strategy, we call this a policy, that will get it the most reward possible over the long haul. Okay, Section 4, From Tables to Brains. So that loop makes perfect sense for a simple little 5x5 grid, right? But how do we make the jump from a tiny taxi game to something way, way more complex, like controlling a robot or playing a video game with millions of pixels on the screen every second? Well, for those really simple games, the agent can literally build itself the ultimate cheat sheet. It's called a Q table. It's basically just a giant lookup table that stores a score for every possible action in every possible state. All the agent has to do is look at its current situation, find the row in the table, and pick the action with the highest score. Super simple, super effective. But what happens when the number of states explodes? Think about a game like Go again. We set it as more possible board positions than atoms in the universe, or even a modern video game, where a single frame of pixels is the state. You can't build a table for that. The cheat sheet would be infinitely huge. It's impossible. And this is where the really big idea comes in. This is the leap from classic RL to modern AI. Instead of that rigid, giant cheat sheet, we give the agent something more like a flexible brain, a neural network. A neural network doesn't have to memorize every single state. Instead, it learns to recognize patterns. It learns general ideas like, in this game, being in a corner is bad, or getting this power up is good. And it uses that generalized knowledge to estimate the best move, even in a situation it has literally never seen before. That ability to generalize, that's its superpower. So when you combine reinforcement learning with these deep neural networks, that's what we call deep reinforcement learning. And what it creates is this amazing hero's journey for the agent. Take this lunar lander, for example. When it starts, it has no clue what it's doing. It just fires its thrusters randomly and crashes and burns over and over and over again. But with each attempt, it learns a tiny bit from the rewards of a soft landing and the penalties of a crash. And eventually, after thousands of tries, it masters a perfect, gentle landing. It literally learns from its failures. All right, Section 5, RL in the real world. So where is this incredibly powerful idea actually being used? Because it's not just for playing games anymore, not by a long shot. It's already out there shaping our world. Today, Deep RL is the magic behind AIs that can beat the world's best players at insanely complex games like Go and chess. It's how we're teaching robots to walk and manipulate objects. Companies like Google are actually using it to manage the cooling in their massive data centers, which saves a huge amount of energy. It's even being used in things like personalized recommendations and helping scientists discover new drugs. And this quote here really nails the core idea, especially when you think about robotics. We're not programming a robot with thousands of lines of code saying, move this joint exactly 32 degrees, then move that one. No way. Instead, we just define the goal. We design a reward function that says, hey, you get a reward for fetching the stick. And then the agent itself figures out the incredibly complex dance of motor controls needed to actually make that happen. Okay, last section, the core takeaway. So after all that, from our little digital pets all the way up to AIs that are changing the world, what is the single most important idea you should walk away with? If you remember just one thing, let it be this. Reinforcement learning is about teaching an agent to hit a goal, not by telling it what to do, but by letting it learn from the consequences of its own actions. And that really leaves us with one final, kind of exciting thought. Now that you get the basic idea that an agent can learn from pure trial and error, what kind of big, complex, real-world problem would you solve with it? What goal would you give it? The possibilities, they're really just beginning to open up.